Yay. Thank you, Imani. It is time for us to learn things. You're going to learn chapter 20 now. Chapter 20 is our last chapter. It's a voltage, current, resistance, and Ohm's law. That's what we're going to do today and Friday. We're not going to get all the way through it today, so I can't give you this homework assignment. But between today and Friday, you guys will do voltage, current, resistance, and Ohm's law, and it will be very good. And then, as we continue in the chapter, you'll learn about electrical circuits. And in this class, we'll only do circuits with batteries and resistors. You'll learn what it means for resistors to be in parallel, what it means for resistors to be in series. You'll learn techniques to simplify electrical circuits. You'll learn a couple of additional rules, Kirchhoff's voltage law and Kirchhoff's current law, to better simplify complicated circuits, and it'll be great. And let's go for it. First of all, voltage. You need to know several things about voltage. Number one, it is a characteristic of a point in space. Do you remember what other recently learned thing was a characteristic of a point in space? From last chapter. What's that? Oh, please. Okay, let's go to the next one, number 2. It is electrical potential energy per unit charge. So you'll notice voltage is electrical potential energy per unit charge. Can you think of something else we learned recently that was something per unit charge that's a characteristic of a point in space?
Electrical field.
Thank you very much, Imani. Thank you for not being part of the conspiracy to not ever answer any of my questions. I appreciate that. Thank you. I know you're on my side. Okay. Number 3, the units, even though electrical potential energy is joules and charge is coulombs, you would think that the units of voltage would be, joules per coulomb. But no siree, we want to honor some guy named Volta, and I don't know anything about him, and I apologize to anyone watching on video. I'm just so ignorant, but I don't know anything about this guy, Volta. But anyway, that's who we named volts after. Joules per coulomb, they are volts. Number 4, or let me depart from this sheet just a little bit, okay? Here, remember volts, which you'll learn later on in that sheet, we call it electrical potential or just potential. So I got electrical potential is electric potential energy per unit charge. Okay, so suppose I have a 12-volt battery. Okay, this is a 12-volt battery, which means this terminal is at positive 12 volts, and this terminal is at 0 volts. To be a 12-volt battery, all that means is they figured out chemically how to make sure that this electric potential energy per unit charge, this point, has an electrical potential energy per unit charge that's always 12 volts higher than that point. That's what they've achieved with a battery. So when we talk about how many volts does your battery have, well, a battery doesn't really have volts. A battery has charge. A battery has a bunch of charge in it. But as far as voltage goes, actually a battery is 12 volts because this point in space is always 12 joules per coulomb higher than that point in space. Okay, so imagine you attach a wire here, and that wire goes to a light bulb, okay? And then the wire comes back to 0 volt land. So it's 0 volts, okay? And imagine I had 2 coulombs of charge exit the battery, light the light, and then come back to the 0 volt terminal. First of all, by this formula, how much energy do these 2 coulombs of charge start with? The fact that you have 2 coulombs of charge located at a point that's 12 volts, that's a 12 joule per coulomb point in space. How many joules of energy does those 2 coulombs of charge have? How many people are thinking, by a raise of hands, how many people are thinking 24 joules? Okay, good for you guys. You can actually just plug in here. I got 12 volts. My electrical potential energy, I don't know, but I've got 2 coulombs, right? So 12 volts, which is the same as 12 joules per coulomb, times 2 coulombs, that's my electrical potential energy. So yeah, I got 24 joules, okay? When this 2 Coulomb charge gets to 0 volt land, how much electrical potential energy does it have now? At this point in space, every Coulomb of charge gets 0 joules of electrical potential energy. So how many joules of electrical potential energy will this 2 Coulomb of charge have when it comes back to the 0 volt land? 0, right? Good. It had 24 joules of electrical potential energy. Now it has 0. Where did those 24 joules of electrical potential energy go? What's that, Imani? Good, whatever it's plugged into. In this case, what is it doing? Yeah, lighting a light. You see? So you see, that's the way electricity works. You started off with a bunch of electrical potential energy. It goes through the motor or the light or whatever you want that electricity, the heater, whatever that electricity does, and then it goes back to 0 volt land, and it used all of its electrical potential energy to do work on whatever you wanted it to do work on. Okay, you guys okay with that? Let me talk more about voltage, okay? Suppose I told you this point in space had an electric potential of 5 volts. Let me get a drink of water. And suppose it's positive 5 volts, okay? Well, just like electric field, if there's going to be a point in space with an electrical field, something's responsible for it. Something's causing it. Whether it's a point charge or a capacitor or whatever, something's causing your electric field. Well, it's the same thing with voltage. Something's causing this point in space to have an electric potential of 5 volts. That is, every Coulomb of charge I put there is going to have 5 joules of electrical potential energy. Let's pretend that there's just some big repository of positive charge over here. And that repository of positive charge, he's responsible for that point in space being 5 volts. So suppose I had some charge here, and suppose it was 1 Coulomb of charge that I had there. Tell me, how much electrical potential energy would that 1 Coulomb of charge have? If it's sitting at a point that's 5 volts? How many are thinking 5 joules? Okay, yay. So the electrical potential energy is equal to 5 joules here. And I'm going to say I start them off from rest. So the kinetic energy is 0. I let this charge go. This charge is going to go, until finally the charge is here. And do you see that this guy's pushing on this charge? This charge is going faster and faster and faster. So let's suppose that at this point, this charge has acquired 3 joules of kinetic energy. How much electrical potential energy would this charge have left? Good, 2 joules, right? Because energy has to be conserved. There's no non-conservative forces acting here. And electrical force is a conservative force, just like gravity. So you tell me, this point in space, remember this is still 1 Coulomb of charge, so that point in space, what's the voltage at that point in space? How many people are thinking 2 volts? Yeah, because a 1 Coulomb charge is there and it has 2 joules of electrical potential energy. So this is a 2 volt point in space. Well, this guy keeps going until finally it gets to infinity. And what's the electrical potential energy going to be when it's infinitely far away from this repository? Say that again, Noel. Yeah, 0. Do you remember what other type of potential energy was 0 when the two things are infinitely far away from each other?
Gravity.
Yeah, gravity. Okay, so sure, at infinity, the electrical potential energy is defined as 0. So the kinetic energy by this point is going to be 5 joules. Okay, so when you're infinitely far away, what's the voltage? Yeah, 0. So by definition, when you're infinitely far away, you got 0 volts. Okay, here's the next thing. Let's suppose I have this point here being 5 volts and that point being 2 volts, and I have no idea what's causing it. This positive repository of charge, let's say we don't even know it's there or we can't see it, we don't know why that's happening. Maybe instead of a positive repository of charge here, I've got some negative repository of charge over there. Who can say, you know? But somehow, for some reason, this point in space is 5 volts and that point in space is 2 volts. Will a positive charge always want to go from a 5 volt place to a 2 volt place if I let it go? Well, I'll tell you, yes. For the same reason that if I hold a mass above the ground, okay, if I hold the mass above the ground, here it's got some positive gravitational potential energy, and here the gravitational potential energy is 0. Objects always fall from a higher potential energy place to a lower potential energy place. It's true for gravity. It would be true even when 2 planets are far away. If these 2 planets are far away, here at infinity, the gravitational potential energy, and I'm going to use the AP exam nomenclature for it, U sub G. Here the gravitational potential energy is 0. What happens to the gravitational potential energy as these 2 get closer and closer together? Like, does it get more and more positive or more and more negative? Think of gravitational potential energy for 2 objects where we're not at the surface of the Earth. Do you remember how gravitational potential energy was equal to negative Gm1 m2 over r? So what sign is my gravitational potential energy everywhere else but in infinity? Hopefully you see negative, right? Negative. Okay, so you've got negative gravitational potential energy. I just want to say again, if you let this go, where does that guy fall? He falls from a higher gravitational potential energy place to a lower gravitational potential energy place. And as he gets closer and closer, that gravitational potential energy gets more and more negative. So I just want you to see again, you're always going to fall from a higher voltage place to a lower voltage place in the same way that you always fall from a higher gravitational potential energy place to a lower gravitational potential energy place. Okay? Here's another thing I want to mention. This is on your sheet. Everything I'm talking about is on your sheet. Sometimes, if you don't know what the cause of this voltage difference is, and frankly, you may not even care, because all you need to know is that there's a voltage difference, right? And so if there's a voltage difference, you are forcing positive charge to go from 5 to 2. You're forcing them. And so there's another name for voltage or electric potential. The other name is electromotive force. Because if you've got a difference in voltages, if you've got a difference in electric potential energy per unit charges, then your charge is forced to move from there to there. And so that electromotive force is making it go in that direction. So if you're in chemistry land, quite often they don't use the words voltage or electric potential. They'll use the term electromotive force. But I'm not sure, do you guys use, so Miss Min doesn't use electromotive force?
No.
In her class? Okay. Does your textbook use electromotive force? Do you
No,
know?
no,
A
it
big
does not.
curly E, a
No.
script curly E thing?
Maybe, but I don't think it's ever been called it.
Have you ever learned an equation called, I think it's called Ernst's or Nernst's equation? Ernst's? Okay, well anyway, okay, well that's good enough. That's all I need you to know right now with voltage. Now, it gets a little trickier when your repository of charge is negative. Let's say I've got a bunch of negative charge here, and I put a positive there. And remember, at infinity, this is 0 volts. Okay? What kind of voltage am I going to have right here at that point in space now? Yeah, it's going to be negative. Now this is going to be negative volts. You know, like negative 5 volts. Why is it negative? Because now this charge is going to naturally go to infinity. If I send this charge to 0 volt land, I'm going to have to do work. This guy does negative work in sending that charge to 0 volt land. Or another way to think of it is, if this is 1 coulomb of charge, okay, then your kinetic energy would have to be 5 joules. If I had 5 joules of kinetic energy, then I could send that charge to infinity land. which means your electrical potential energy ends up being negative 5 joules. Okay, and that's what it means. If I've got a positive charge at a negative volt place, then it's got negative electrical potential energy. So now, you know, your electrical potential energy starts looking like gravitational, where you get these negative gravitational potential energies, and you can have negative electrical potential energies when you have a positive charge residing at a negative volt place, or a negative charge residing at a positive volt place. Then in both scenarios, you now have negative electrical potential energy, which means you require a kinetic energy or someone to do work to send that charge to infinity. All right, well, hey, you know, I don't know, I hope that's helping a little bit. Oh, I don't want this sheet. Let me continue on. So we talked about electric potential or potential. We talked about positive charge always going from a high voltage place to a low voltage place. Because of voltage difference causes charge EMF. Okay, example 1. Hey, I would like everyone right now to please do example 1A. Let's see how many of you can do this without any prompting from me. And you're just going to mindlessly use voltage equals electrical potential energy per unit charge.
Hey, Mr. Shana,
Yes.
how many volts is in a lightning bolt?
Oh, you know, that's a good question. I think it's like 1,000,000.
How about coulombs?
Well, that's the problem is it's got a lot of coulombs. It's like, I think I read it was like 2 to 5 coulombs. So you got 2 to 5 coulombs, but in 1,000,000 volts. So then now you're getting 2 to 5 million joules of energy that strikes in a moment, in an instant. And so that's just a stupendous amount of energy. Yeah. Yeah, so that's why lightning is so bad.
It's
Yeah.
cool though.
Okay, what is that? Electrical potential energy. And what did I say? It was 2 coulombs? And so I got 10 joules. Okay, how many people got, for part A, how many people got 10 joules? Okay, yay. Any question or problem on that? Okay, now I'd like you to do part B. I've got a charge, it's 2 coulombs of charge that's going to travel from a 5 volt place to a 2 volt place. Okay? So it's going to lose electrical potential energy. But let's assume that the kinetic energy remains the same. Let's say the kinetic energy started with some small amount of kinetic energy and then ended with some small amount of kinetic energy, so the kinetic energy didn't change. Please figure out how much work must that charge have done if the kinetic energy didn't change as it went from a 5 volt place to a 2 volt place. Yeah. So here we go. Here's a formula. This is a formula from chapter 19, which you don't need to know per se, but I want you to be aware of it. It turns out the charge multiplied by the change in voltage ends up being the work done. And the change in voltage is really weird, is the difference between what you started with and what you ended with. And so this is a 2 coulomb charge, and the change in voltage is positive 3 volts. That is, it started with 10 joules of electrical potential energy and ended with 4 joules of electrical potential energy. So the change in voltage was 3 volts. But anyway, that's your work, and so you end up with 6 joules. And how many people got 6 joules? Okay, many of you. And however you think about it is fine. You know, you can think of it as Q delta V, or you can think of it as I started with 10, I ended with 4, I lost 6 joules. Where did those 6 joules go? Hey, it went for work. Okay. Alrighty, please do example number 2. Good luck. Okay. What did you guys put as the voltage or the voltage difference? Yeah, 10 volts. You're going from a positive volt place to a positive 5 volt place to a negative 5 volt place. The voltage difference is actually 10 volts. So it ends up being the change in voltage that we really care about. And it does 50 joules of work. You know, because electrical potential energy, we can also say it's the work, Q naught. And so I got Q naught equals 50 joules over 10 joules per coulomb. So I got Q naught equals 5 coulombs. Any question or issue on example 2 that the answer is 5 coulombs? And I have to say, this level of understanding is good enough. You know, I mean, I know you guys aren't expert because we didn't do chapter 9, but this is for doing chapter 19, I mean. But for doing chapter 20, this is good enough. Hey, it is time to learn about current. Please look at your sheet on current. Number 1, it's the flow of charge and it is called by the capital letter I. Number 2, current is charge per time, coulombs per second. It's like this sort of thing. If I have a battery and I have a wire going from the positive terminal to whatever it is that I'm doing, maybe a light bulb, I'm going to do a light bulb again, okay? And let's say this was 12 volts and this is 0 volts. Current would be like a guy here counting charge and he has a stopwatch. And he goes, okay, I want to count how much charge goes by me per second. He's not clocking speed. He doesn't care how fast the charge are physically going. He just wants to know how many charge are going by him every second. You see? How fast the charge are actually moving doesn't really matter to him. And in fact, I think when you have a current carrying wire, I think the actual charge is moving at like 5 meters per second or something. So the charge itself is not moving that fast. But we don't care how fast the individual charges are moving. We just want to know how many charge get by him every second. Well, that's coulombs. That's current. And the units of current is coulombs per second. But we want to honor this guy named Ampere, although we pronounce it ampere here in the United States. And so it's amperes, amps. Okay? The third thing you should know about current is you need a circuit for charge or current to flow. Okay, this guy is counting the charge as it goes by. Well, what if I remove the light bulb from the circuit? Is current still going to go by him? No, because the current gets stopped here. And just like a river, if you dam a river, the river doesn't keep flowing until it reaches there. In no time at all, the river is a lake. In no time at all, the river doesn't flow at all. If no river can go past this point, then no more river will flow. Or it's like a traffic jam. If you completely block the freeway, in no time at all, you're going to have a mile of cars that are stopped. Okay? You don't get current when there's an open circuit. You don't get current if you don't have a circuit. And I got to tell you what a circuit is. Have you ever heard of something called like a circuit court? like the Ninth Circuit of Appeals, federal court, that's what we have here in California. And that comes from judges that used to be called circuit judges, where they would start in one city, and then they would ride to this city, and that city, and that city, and that city, and that city, and then finally come to their home city, and then just do it over and over again. They would ride the circuit, and a circuit is a complete circle. A circuit is a complete path, where you end up where you started. Well, current can only flow in a circuit. Your current has to have the ability to start and end in the same place. You see what I mean? So you can't have current if you don't have a circuit. Okay, let's go ahead and do example number 1. Part A. You've got a 3-volt battery providing 0.17 milliamps. And by the way, a milliamp is a thousandth of an amp. That's normally the unit of current that you see in real life is milliamps. If you're doing microelectronics. If you're doing power electronics, you'll see amps. But for the stuff we do, it's milliamps. So that's 0.00017 amps for 5 minutes. Find the total charge that flowed. So please do part A right now. Part A, you're going to use that formula. Current is coulombs per second. Current is charge over time. Tell me, because amps is in coulombs per second, those 5 minutes, am I going to have to convert those to seconds?
Yeah.
Absolutely. So 5 minutes is 300 seconds. So 300 times that is, so I got 0.051 coulombs equals the amount of charge. How many people got 0.051 coulombs? Oops, like 6 of you. Any questions or problems on that? Because now I'm going to have you do part B. And part B, you're going to have to use this formula right here. So please do part B now, using volts equals work over charge, or volts equals energy over charge. Excuse me. This is a 3-volt battery, and the charge is 0.051 coulombs. So that's how much electrical potential energy it started with. It ends with zero joules of electrical potential energy, so it must have donated all of its electrical potential energy to do some work of some kind. How many people got 0.153 joules? Yay, yay for all of you. Okay. Hey, that's voltage and current. Let me end with one more analogy about the relationship between voltage and current. And the analogy is going to involve a waterfall. Okay. Here we go. Imagine I have a waterfall, and here's my water, okay? And my water right now has two types of energy. It's got kinetic energy because the water's in motion, and it has gravitational potential energy. In fact, it's got a whole bunch of gravitational potential energy, okay? It's got gravitational potential energy, lots of it. Well, analogously, if this were charge, then we'd say this is a point in space with a high voltage, electrical potential energy. But we don't talk about electrical potential energy like we do gravitational potential energy. We talk about electrical potential energy per unit charge, because it's just a lot more convenient. Okay? So we'd say that this charge has a high voltage. Now this water falls, and suppose I put some, paddle water wheel here, and that water wheel was attached to something, maybe a mill to grind grain, or who knows what it's attached to, but it's doing work for me of some kind, okay? And then this water ends up splashing, just smashing into the water down here. And so this water will do work on this water here. The water it slams into, it'll raise the temperature of that water a little bit. It'll make the molecules of this water go faster. Maybe it'll make the bottom of this bed deeper, or maybe it'll swirl around a bunch of rocks and do some erosion. Who knows what it does? But all of that energy gets spent in doing work. Does my river stop flowing at this point? No, it's still flowing. In fact, it's probably still flowing at a somewhat similar speed as here. So you haven't lost any of that kinetic energy. In fact, the kinetic energy is probably insignificant compared to this huge amount of gravitational potential energy it had. So the water keeps on flowing and flows down the river. And maybe it'll hit another waterfall and do some more work for you. Well, the point is that this water flow, the flow of the water, is like current. You don't lose current when work is done. It's almost, it's non sequitur. How fast does the water flow? Well, not that fast, I guess, but boy, it sure had a lot of voltage. It sure did a lot of work. But the water doesn't stop flowing. And so I want you to see that in order for a battery to do work, it's got to be able to have current flow, and that current has to keep flowing. If the current stopped flowing, then water stops moving, then you get no more realization. Your water wheel's not spinning anymore. Water isn't falling over the edge if you do some open circuit somewhere and the water doesn't get the flow anymore. As long as that water's flowing, you get work out of the water falling off the waterfall. As long as this current is flowing, you get work from this charge going from a high voltage place to a low voltage place. Well, I hope that's making sense. Any questions? All right. Well, as you do more, you'll get more and more intuition. And we'll complete this on Friday. Tomorrow you get your big test. And good luck, you guys. So at this point, I say bye-bye.